Hello friends. So today we are going to discuss about a new topic, that is isotopes and radioactive decay and its applications in biology. So before going to see what are the applications of radioisotopes in biology, we will see a small introduction about isotopes. Then after that, in another video, we will discuss about the radioactive decay, its calculations, then how these isotopes are used in biology applications like that. So in 4 videos, we will be completing this topic. So in this first video, we are discussing about isotopes. So what is isotopes? Isotopes are atoms having same atomic number but different atomic mass due to change in the nucleus. So how a change in the nucleus is happening? So change in the nucleus is happening because of different numbers of neutrons. The element will have same atomic number, but the same element will have a different atomic mass or atomic weight due to difference in the number of neutrons in the nucleus. So if an element is existing in the universe, it will be a mixture of radioactive and non-radioactive elements. For example, if I say magnesium, so there will be magnesium 24, there will be magnesium 25, there will be magnesium 26, which will be distributed like 78, 10 and 11% respectively, like that. So it will be like that, it will be distributed in the universe. So if you take the chemical properties, so suppose if you have magnesium, and in that magnesium you will have all these different types of isotopes, but if you use them in a chemical reaction, you won't see much difference because the chemical properties are determined by the atomic number. So because of that, we won't see any difference in the chemical properties of the element because of the different atomic mass. So even if there is it is incorporated in the biological molecules, it will be introducing only a very small difference in the molecular weight. So because of that, it won't affect any of the biological functions. So most of the radioisotopes used in biochemical studies are beta and gamma emitters or beta and gamma emitters. Sometimes it can emit only beta or only gamma, or sometimes beta and gamma, both. So depending on the disintegration. So the main elements which are used in the biological research are carbon-14, P32, P33, S35 and tritium or beta emitters commonly used in biological research. C14, if you see, it is used in carbon dating for determining the age of a material. P32 and P33 are used in molecular biology work, especially in DNA works. S35 also used in DNA works for DNA sequencing. This tritium are used in biological function assays. So most of the naturally occurring and man-made isotopes are unstable, and because of that, the nucleus will be undergoing different types of decay. So there are different types of decay modes. So isotopes are unstable, and the nuclei decay to more stable forms by one or more of the processes and are known as radioactive isotopes. So these radioactive isotopes, if you see, there are different types of decay process. So there are beta particle emission, positron particle emission, alpha particle emission, electron capture, and particle emission followed by transition. So if you see, there will be transformation of the nucleus also. In the case of beta particle emission, you will see there will be a change in the atomic number of the resulted molecule. There will be one increase in the atomic number, but the atomic mass will be same, and one beta particle is emitted. And in the case of positron, if you see, there will be a reduction in the number of atomic number of the resulted nucleus after disintegration, but the atomic mass will be same. And in the case of alpha particle emission, you see there will be reduction in the atomic number by 2. Suppose if the atomic number of the element is 4, the resultant molecule will be having a atomic number 2, and the atomic weight also will decrease by 4. Suppose if the molecular atomic mass of that element is 8, the resultant molecule will have a atomic weight of 4. So there will be reduction in atomic number by 2, and there will be there will be decrease in atomic weight by -4. In the case of electron capture, if you see, there will be a gamma emission will be there. Then along with that, the atomic number of the resultant molecule will decrease by 1, but the atomic weight will be same. And in the case of particle emission followed by transition of the molecule, there won't be any change in the atomic number or atomic weight, but there will be a gamma emission will be taking place. So this is the different types of decay modes. So based on this only, we will be further using or we will be calculating how radioactive material can be used and how it can be used in biological function, and how it is used in biological function, how we can use it for the different calculations like that. So there is units of radioactivity. So based on radioactivity, based on radiation loss, and based on absorption. So the first one is Curie. So that is 3.7 into 10 to the power 10 disintegrations per second taking place in the nucleus. It's a non-SI unit which was introduced in 1953. It is also said as a 2.22 into 10 to the power 12 disintegrations per minute. Becquerel is an SI unit for measuring unit of radioactivity. 1 becquerel is equal to 1 radioactive decay per second, which is equivalent to 2.703 into 10 to the power -11 Curie, and it was introduced in 1974, and its units is per second. Unit of radioactive dose, that is Röntgen, that is ESU per 0.001293 gram of air. It was introduced in 1928. It's a non-SI unit, and air per gram it was introduced in 1950. So these are 1 Röntgen is equal to 1 air per second. So this is the unit of radioactive dose, and the unit of absorption for physical dose, that's rad and gray. Rad is a non-SI unit, which is equivalent to 100 air per gram. It was introduced in 1953. It's a non-SI unit. Gray is a SI unit, which was introduced in 1974. That is joules per kg. And biological dose, how you can measure the absorption, that is a RUM. That is a non-SI unit. Sievert is a SI unit. RUM is again 100 air per gram. It was introduced in 1971 as a non-SI unit. Sievert is a joule per kg. It was introduced in 1977, which is an SI unit. So these are some of the radioactive elements which are used in the biological assay. That is calcium 45, carbon 14, cesium, chlorine, chromium, cobalt 60. So you can go like that. So the number indicates the atomic mass, and half-life, that is the one which is determining the how much element is how many days are required or how many years are required to become the half of the radioactivity. So that is all. So this half-life is very important to calculate many of the biological values when you use this radioactive material in the biological assays. So one can use this as a reference. So that is the thing. So thank you for listening this video. Please continue and watch our other videos also on this. radioactivity. So please subscribe our channel, share our channel, also put the comment box, like our channel. Thank you very much.